Can you see the screen?
Yes, sir.
So in this part of the lecture, we are discussing with the free vibration response. So here we are initiating and starting with the response of the system. So what is the response of the system, and how to compute the free vibration response? You know that when any structure is initially displaced, then definitely after that the studying the response of the system after that vibration is important, because this is also applied in the civil engineering. Sometimes the force is continued, but when the force is stopped or once the initial displacement is already made, then you want to see that what happens if you displace the structure initially and how it behaves. So therefore, in this case, we are discussing about the response of the system subjected to the free vibrations. And undamped free vibration will be studied, and the response equation will be proved. And then at the end, I will explain about the MATLAB program, how to develop that and how to use it, and 2 or 3 numericals related with the free vibration response. So you know that for a single degree of freedom system, the equation of the motion is a linear second order differential equation, and this can be written as mu plus cu plus ku. And the various methods for the solution of the equation of the motions are classical solution to Hamel integral, frequency domain method, and numerical methods. So there are different methods which are available, and basically you are able to compute the response of the system. Now the point is that advanced and we are not going into the detail of solution of the equation of we want to so that just so the vibration of a system initial disturbances, initial displacement or velocity without any external force is called free vibration. So here you can u plus cu plus ku is equal to 0. So this is called as the free vibration because the force is equal to 0. Previously we have developed the equation of motions today, and here you can see that the force is equal to 0. So the equation of the motion becomes homogeneous second order linear differential equation. So in case of the free vibration, this will be the equation of the motion, where the force will be equal to 0. So it is a second order linear differential equation. The second response is important because many practical systems are excited by initial disturbances, and you know that in civil engineering also, if there is a ground displacement and the building is vibrated initially and suddenly the earthquake stops, but building keeps on vibrating. So therefore, the application of this topic is understood in the civil engineering. Complete solution of the force vibration also include the free vibration component. So also the complete solution of the force vibration with the force vibration, there are two components. One is the free vibration component, and one is the force vibration component. Now we are going to prove the response of the system when it is under the effect of the free vibration. So undamped free vibration. When you are talking about the undamped, it means that the C value, this value is 0. So the left equation of the motion, which is left, is mu plus ku, which is equal to 0. Now in the reality, there is no existence of the undamped system, although in civil engineering, all the structures are partially or somehow they are damped system. And we can consider 1% or very small value of the damping, 2%, up to 5% damping can be considered. However, the response gives an insight into the nature of the damped system. Basically, undamped system we are studying first so that we can just exclude the effect of damping, and the same things will be discussed with the inclusion of the C. So first you must prove the different relationship and see that what happens when the system is undamped free vibration and subjected to the no force but free vibration is studied with some initial displacement or initial velocity is given and how the different graphs between the displacement versus formed. You know that generally the solution of U can be represented in terms of g raised to power e lambda t. Normally, U, the response of any system that initially we have to assume some that how we can represent the response. U is basically the function of the time. And for proving the relationship, you initialize that, let's say, the U is equal to, U value is g e raised to power lambda t. So we can substitute this solution into the equation of the motion. Now you know that the U is equal to g e raised to power lambda. Derivative, first derivative, what will be the first derivative? U dot, that is not needed, and then you compute the second derivative. So first derivative will be equal to lambda into e raised to power lambda t, and second derivative will be lambda square into e raised to power lambda t. So taking the second derivative and putting here in this equation U double dot, it becomes G lambda square M e raised to power lambda t already here, G e raised to power lambda t, and K is already there and M is already there. So putting the values and equal to 0. Now you have to solve the roots of the equation. The coefficient of the e lambda t is basically lambda square M. Because the g and e raised to power lambda t, it becomes 0. It is a common in both. So it means that this implies that your coefficient of the roots of this equation will be lambda square k is equal to 0. You know that k is basically equal to, if I divide whole equation by m, in this part, I divide the equation by m, so it will be lambda square plus k over. So after that, the next equation is lambda square after dividing it by m plus k over m is equal to 0. Now you can write down the, you know that the k over m is the circular frequency of the system, that you have already studied that k over m is basically the omega, the angular frequency. So therefore, you can replace the k over m as a omega square, because under root omega is equal to the circular frequency. So the roots become lambda square plus omega square is equal to 0. So this implies that the unknown values of the roots are lambda is equal to plus minus iota, because when you take the under root and it is a minus omega square, lambda square from this equation is lambda square is minus omega square. So it means that the roots which are computed as plus minus iota. Now you can put down the value of the root once with the two roots are obtained. So you can be written as the in terms of two parameters. You can be represented as in terms of two parameters, g1 e raised to power the first root plus g2 into e raised to power minus I omega t, because one time it is iota omega t and one time it is minus iota omega t. So therefore you can compute it the root. But you know that in the trigonometry, e raised to power I theta can be represented as the cos of omega, cos of theta plus. So therefore, e raised to power it plus e raised to power minus I theta, you can write the roots in terms of cos omega t and sin omega t. So finally, the response of the system can be represented by this equation, where a and the b are the modified constants which are needed to be determined. So when you replace the values, you can write down the response as a cos omega t plus b sin omega t, and you have to determine the a and b values. So let's say now u value is sin omega t. Now the T constant A and B are determined from the initial condition, because you know that when you put the T value 0, let's say the U naught, the initial value of the displacement U at T0, U naught become the U naught, and the velocity, initial velocity is equal to V naught. Now, when I put the U equal to 0 and the T value equal to 0, so this comes out to be A cos of omega T cos of 0. So answer is and B sine of 0. So sine 0 is cancelled, and when you put the value of U equal U at T as the U naught at time 0, and it means that by solving this equation you can get the value of the A as a U naught. Why? Because cos 0 is 1 and sine 0, this B is eliminated. So from putting the value, first solution, when you put T is equal to 0, the answer is A is equal to U naught. Now the second solution, you take the derivative of this component. Take the derivative U naught. So when you compute the U dot, the derivative of this becomes the minus A sine omega T plus omega minus A omega sine omega T plus B cos omega T. So by putting the value of again at the time T0, when the you can find out another constant, which is B, because again when we put the 0, the first it is eliminated, the first one, and the second one become the B cos of omega T. So putting the cos as 0, cos 0 it is 1, so B is equal to and the second time you say that the U naught is there on the left side, because it is you are solving the derivative. So the answer is B is equal to, you can write U naught initial value as the initial velocity at time 0. So V naught, and because the derivative of this was the B omega sine omega T cos omega T, so that's omega is divided. So you are, after solving and applying the boundary condition, the two constants are solved, which is A and V, and finally you can represent now the equation when you all the parameters are solved. You can represent the equation at the U naught cos omega T plus this is the U naught, putting the value of A and putting the value of the B, V naught over omega, put down the value in the initial equation, and then this is the final response of the system. So this is the first response that you studied. In the dynamic classes, we have to study the response of all the system, and this is called as the free vibration response. So you have to save this formula with you, and you can apply this formula to find out the response of the free vibration. This response ut is equal to U naught cos omega T plus V naught over omega sine omega T. Now if you solve this and take you want to compute the amplitude, the maximum displacement. So you know the coefficient, when you scale this value, maximum displacement can be found by squaring this value coefficient. So and this can be written as U naught cos of theta plus V naught over B sine of theta. It can be also written as rho into sine of omega T plus phi. This is another trigonometry, that this can be written as rho sine omega T plus phi, where rho is the amplitude. Rho is this amplitude of the system. So this is a free vibration response graph. You see that there is no damping. So what happens that your amplitude is not reducing. It is even the time is infinity, your amplitude is not reducing. It means that you can determine this value of the amplitude using the this equation, and this amplitude remains constant. The reason is that no damping and no dissipation of energy, and your response is basically maximum response remains same. So this response can be computed by U naught square plus V naught over omega square, and if you want to compute the angle phi, initial angle phi, so that will be equal to U naught omega over V naught. And V naught is basically the derivative of this equation, because this is U, and if I take the derivative of the U or take the slope of this du over dt, if I take the U over t or take the slope of the equation at initial point, this becomes the initial velocity. And one complete vibration is basically the time to complete one vibration is 2 pi over omega, and the number of vibrations per second is basically the frequency that is inverse of time. So from this, we are able to get some new relations. One is the omega that was k over m. Then if you want to see the time period that needed to complete one vibration is 2 pi over omega, and the next one is the value of the frequency. Frequency is the number of vibrations per second. So this response that is shown in the red color is basically the response of the system that you plot when you put down this equation, rho sine omega t plus phi, or either you take this equation, u naught over cos omega t plus v naught over omega sine omega t, you can get the response of the system. So this is the free vibration response. Now the point is that there can be different conditions, because this response that you are watching here, the response that you can see here is basically this response is basically the response u naught initially is present. So now you can see that what is the response when the initial conditions are changed. Here the u naught was present, so this is the response, and the response can be obtained. This is the case when the now another free vibration response is indeed very helpful to determine the time period and frequency of the system. And how can you determine the value of the time period and frequency when the spring mass system is hanging and the initially displaced equal to delta st? So when any initial displacement is given equal to delta st, you can see that W is equal to K into delta St. So this W is equal to mg, and mg is equal to K delta St, and K is equal to you know that this W is equal to mg force, but at the same time this total weight is equal to the stiffness into displacement. The total downward force is also equal to the upward force which is developed in the spring. This force Fs is equal to K into delta St. So it is whereas W is equal to mg. So by putting W as mg and force as K delta St, the K of this hanging system can be determined. So one thing is that from the free vibration you can determine the value of stiffness. Now if you have the K value, you can determine the omega. Omega is equal to K over m, and putting the values of the displacement as the K as mg over delta and divided by m, you can determine the omega, the angular frequency of the system. And from that you can determine the time period, because time period is 2 pi over omega, and you can determine the time period of the system. And the natural frequency of the system, because omega is in the radian per second, but the natural frequency of the system is in cycles per second. So you can convert that into the natural frequency of system by 1 over t, or omega over 2 pi. So you can also get the value of the frequency. So free vibration response is helping us a lot. We can determine the stiffness, we can determine the angular frequency, the time period, and the natural frequency of the system. Now the next thing is the plotting of the different things, like how to plot the different variables, and how you can see the different initial conditions are changing, let's say, and how to plot it. So the free vibration response, the equation is this one. If I take the derivative of u naught, the answer is rho omega cos omega t plus phi. So this implies that the omega can be here. So u naught over omega is equal to this one. Now if I take the square of u square and u naught over omega square, if you take the square of this equation plus the square of this equation, the answer is only omega square. So we want to plot it and see the interesting result. How you can plot it? You can time is variable, omega is known. and you can plot the system equations. U as the phase angle phi is known, and you can determine that phi angle. And now you can plot the system. This one is the vibration response of the system when you are plotting U versus T. And when you plot U and U naught over omega, when you plot these two values, U, this is U naught actually, I think. U and U naught over omega, when you plot it, you get the circular answer. The answer for this response is a circular. And when you plot U naught omega versus T, this is the derivative of this one. U naught over omega is basically, when you plot this one, this is somehow different because it is V naught over omega initial value, and it is a U naught over omega. So when you plot this value, this response is different. So amplitude is the maximum value that is basically equal to U square plus U naught over omega square at any instant. So this is the response of the system when it is a free vibration response, and different quantities are plotted, variables U versus T, U versus U naught over omega, and U dot over omega, and U dot over omega over time. So you can see the response of the system, and when what is the velocity response? This is the velocity response, this is the displacement response, and this is displacement versus velocity response. The second response is when there is not velocity, initial velocity is 0, but displacement is present. So U naught is 0, U naught is present. Here the both were present, V naught and U naught both were present. In this case, U naught, the velocity, why velocity is 0? Because the slope of the line at 0 point is 0 degree. The slope is telling you the velocity value. So if the velocity is not present, but only displacement is present, then when you put down the values in the equation, you know that rho is equal to this one, and that comes initially the amplitude will be equal to the U naught, and tangent of the phi, when you compute this, V naught is 0, so answer is infinity, and phi, it means that the angle is 90 degree. This angle is with the vertical is 90 degree. Because when you take the slope, the angle is also, phase angle is 90 degree. And U is equal to, now the plot the function U will change. When you put down the value, the function can be plotted, because rho, you know that the U is rho sine omega t plus phi. So when you put down the values of the rho and the other values, this is the answer, U naught cos of omega t. Now you can also take the derivative of this, and the answer is U naught over omega, U naught cos of omega t plus phi. Taking the derivative of U, this gives you this answer. If now you have all the equations again, which equation? U equation, then the U naught over omega equation, and the time also. So you can vary the time and plot these three functions, one function, the second function, and the third function, and the result are somehow different because it is starting from the 0, velocity was 0 initially. So unlike the previous case where the velocity was present in the previous case, in this case the velocity should be 0 at the start. And similarly, it is a circular, but rho is basically the equal to the radius of this, and the phi will be, this will be the phi angle of that. So you can plot the U versus U naught over omega, U naught omega over and t, and U dot U versus the time. In this way, you can also see the response of the system with initial 0 velocity. Third is the response of the system with initial 0 displacement, but not the 0 velocity. So this response is also interesting because in this case, you will compute the response of the system with 0 displacement initial and 0 displacement with non-zero velocity. So it means that U naught is equal to 0 value, but U dot naught is not is equal to V naught, and in that way you can compute the amplitude. Amplitude can also be computed, rho as U naught square plus V naught over omega square. You know that, and the answer is only V naught over omega. And similarly, you can compute the angle, because this tangent phi will be 0. So phi angle will also be 0 in this case. And the next one is the U. So response of the system will be this, and the derivative of that U is this answer. You can plot this value u versus the u naught over omega u versus t and u naught omega versus t. So all these values can be plotted and you can see the behavior of the system, that because the velocity was not zero and the displacement was zero. So here you see the displacement is zero here, but at the same time the velocity is present. And this plot can be interlinked because you know that this is the amplitude. So this should be amplitude, in this case rho value is v naught over omega, and when you plot this value, that is same all the time, the maximum amplitude will remain v naught over omega. So in this way you can get an idea that what will be the happening to the structural system when the velocity is not zero and the initial displacement is zero, and what is happens when the initial displacement is zero but velocity is not zero. Now the things when there is an impulse also, this is the another case when there is some extra vibration is given, which is not part of the system, but how this will affect our system. When some extra initial impulse is generated, impulse is basically equal to the mass into the velocity. So when the initially there is some impulse value, what happens that you have the rho 1, there is a two separate rho 1. One rho 1 is because of this value, and another one is because of this value. So there will be the second there are two kinds of response will be there. Some students are waiting in the lobby, so please admit those students. Can you see the screen? Can you see the screen?
Yes, sir. Yes, sir.
Yes, sir.
Response of the system when the impulse is present, and what happens that you can determine the response of the system when there is a impulse. So this is a bit different problem because there is a two responses, one when rho 2 when the impulse was there, and rho 1 when only the u naught and v naught or omega are present. So in this case also the formula will be slightly modified because when the response is for the impulse, this have the different equation, and in this zone the equation is this one, and in the other zone the equation is this separate equation of this zone. So this is the case when initially you disturb the body by some impulse and again the free vibration started. So we have studied the four response of the free vibration. One is the one vibration. Initially, I told you about how the equation will change, how to determine the response, what are the boundary conditions, and how you can determine the value of the u, and what is the role of this, and what is the advantage of this these expressions, because you are able to compute the stiffness and the time period and frequency, and then the response of the system for initial value of u naught and v naught, and then the response of the system with zero velocity, then the response of the system with the zero, response of the system with the impulse. There is the response of the system when you have the ground motion. You have the ground motion. So then you know that velocity is not present, but only the ground motion is present. So amplitude of the system, initial amplitude that is given to the system is the ground displacement. So only the rho value is the ground displacement. So when the ground displacement is given, then what happens that the angle is equal to 3 pi by 2, and when you see the response of the g some omega t plus 3 pi by 2, and then you can putting the value ug, taking the common 1 minus cos of omega t, so you can determine the response of the system uh, when the system is displaying ground vibrations. So in this way, you are able to compute the different response of the system subjected to the ground response. So this is a UG, which is a ground displacement, and it will displace the building. And then what happened at velocity is 0. So amplitude becomes UG. And now you put down the values of the rho cos omega. The total response will not equal directly UG sine of omega t, but UG plus UG sine of omega t, because everywhere UG is added, like we have done in today the problem. Some of the displacement have to be considered. The ground displacement plus the response of the system due to the ground displacement. And finally, you can plot the system. You see that velocity becomes 0, and this is the response of the system subject to conditions. And what happens, that amplitude is the same rho value, but when you plot the value, phi comes up 3 pi by 2. So this is the response of the system subjected to the ground motion. Next, we are doing the problem. Please read down the problems now. Some book problem. Based on this lecture, you can plot the response, but first we will do the problems, and then I will explain how in the MATLAB you can work on it. So please read this problem, and this is from the book, and you can solve it. Please solve this problem in next 5-10 minutes. First, note down the data. So a steel frame which is shown in the figure having a rigid horizontal member to which horizontal dynamic force is applied as part of the overall structural design, it is required to determine the natural frequency of the structure. Two assumptions are made. The masses of the columns are neglected. The horizontal members are sufficiently rigid to prevent the top of the column, prevent the rotation. These assumptions are not mandatory, but we can simplify the problem because there will be no degrees of freedom present inside the beam, no rotation. This will be simplify our analysis. Normally in the civil engineering structure, we are interested in the response at the top node at story level for earthquake load. So this is the problem. You have this frame structure. You have the U value, you have the lateral load which is 0, and this is the total load. These are the section, this is the length. And this system can be represented by spring mass system with zero damping. So what are the requirements? You have to determine the stiffness of the structure, you have to determine the time period and frequency of the structure, and then you can basically solve this problem. This is not difficult, it is a simple problem. You have the total weight on the top of the beam is 5005 because the length of the beam is 25. The total weight acting on the beam level is 5000 pounds. The moment of inertia you will see for the given columns, you can see the moment of inertia for these columns or it is also given. So this is the moment of inertia. The E value for the steel is 30 into 10 to power 6 psi. Now what is the stiffness when the top of the beam is rigid? In this case में क्या stiffness आती है? So the stiffness is 12 EI over L cube. This is the stiffness in this case. So you can compute the stiffness. Why this is multiplied by the 2? Because there are two columns. So the stiffness can be computed, and the K is 12 into EI over L cube. So you can compute the stiffness also. Now you have the stiffness, you have the W value, you can compute the frequency of the system. So the frequency can be determined as 1 over 2 pi into kg over W, where K is the stiffness, G is the 386 inch per square second, and W is, I told you that mass K over M, so M is written as W over G, where W is in pounds and G is in inch per square second. So you have this building will generate the 4.46 cycle per second, and you can determine the time period as 1 over F, that how much time it will take to complete the one vibration. So in this way you are able to determine the stiffness, time period and frequency of the system. You can solve the many different parameters by the formulas that we proved today, and by the free vibration response you are able to plot the different things. So it is really helpful while you are solving the different structures. Please see this next problem now and try to solve this problem. Can you solve this problem? Yes, you are not telling me anything. Can you solve this problem? Yes.
Sir, we will try.
Ji?
सर हमें टाइम पीरियड दिया हुआ है इसमें, उससे हम निकालेंगे इसकी फ्रीक्वेंसी और फिर फ्रीक्वेंसी के फॉर्मूले में इक्वेट करके के निकाल सकते हैं.
There are two cases, one when the tank is empty and one with the tank is full. So when the tank is empty, what will be the frequency? 2 pi over Te. The tank is empty, so you have the stiffness is a material property, but weight is unknown. So you can write down the equation A when the tank is empty case as WE omega E 2 pi over Te. Omega is basically different than W, so omega is equal to 2 pi over time period, and you know that the time period is equal to 1, and you also know that omega is equal to K over M, where M is equal to W over G. So you can write down this equation to this one, and this is the first equation. Now the second equation, when the tank is what is the weight of the water, because 5,000 gallons, 1 gallon is equal to 8.34 pounds. So total weight of the water is 41,700 pounds. Now when the tank is full, you can again write the equation of the omega. Omega is equal to 2 pi over Tf when the tank is full. What is the time period? There is a one mistake, because the tank is full, the time period was different. So it was a 2.2 second. So the time period is 2.2 here. So 2.2, and then you solve the equation kg, because now the weight is not same, because when the tank is empty, the tank weight is W. Now the water is added, so the weight will become W plus 41,700. Weight will modify and weight will change. So you will again rewrite the equations, and now equating these two, because you know that the stiffness is same, and you can take the sum of taking the squaring the equation on both sides. So take squaring this equation and this equation, squaring this one, and then squaring this equation. You can determine, and then dividing it, squaring the equation and then left and right side, and then dividing equation 2 by 1. So you can have the 2.2 square or 1 square, like because आप इक्वेशन क्या बनेगी, 2 पाई ओवर टी एफ एक इक्वेशन बनी इज इक्वल टू दिस, और एक इक्वेशन बनी 2 पाई ओवर 1 इज इक्वल टू दिस. इन दोनों को स्क्वायर करें, पाई पाई से कैंसिल, और डिवाइड भी आपस में करें. तो पाई का खत्म हो गया रोल, एंड द वेट इज लेफ्ट kg, and all those are also cancelled. Stiffness is cancelled, so left is the weight. So from this equation you can determine the weight of the, what was the W? W was the weight of the empty tank. So you can determine the weight of the empty tank in this way. And next you substitute the value in the equation. Now आप इसको value को W and G value can be put back into the equation number 1 to find out the K value. So what is the stiffness of the tank is 1110 pound per inch, and what is the weight of the tank, that is 10,860. So actually the free vibration is very helpful because any practicing engineer have the eccentric mass vibrator and they vibrate the building and take some readings of the frequency and the vibrations. They note down the values and then they are able to compute the stiffness of the different structural components. So this is the application that you are doing for this topic. So these two problems are there, but you can see many other problems from the book also. These are also from the book by the Mario Paz, and you can plot the response also. So try plotting the response of the system also. Now next phase of the lecture, we will study about how to plot the response of the system. I want that you are able to plot the response of the system, U versus T. How you can obtain this response when you have the equation, when you have U value in terms of time, and you have all the values here. So can you plot the response of the system? This one, and this one. So try plotting the different graphs yourself in the MATLAB. So I can guide you one software program in the MATLAB how to initiate that, and then you should work for the all the different plotting for these functions into the MATLAB. Or any other software you can use. Python, you can use Python or the MATLAB or Excel. Can you see the screen now? Visible है screen?
Yes, sir.
Yes, sir, visible है.
Now response of the single degree of freedom. Next is the response of the single degree of freedom using MATLAB program.
Yes,
This
sir.
is our design class today. Briefly, I will explain. Normally, you have the laptop with you, and the MATLAB should be installed in your system so that you can plot the response of the single degree of freedom system. Initially, आप क्या करेंगे? What will you do? That you will clear all in the MATLAB program CLC clear screen. Now this yellow color is automatically when you put the percent sign, because when you are writing the program तो आपको अपनी guidance के लिए इनको remarks line कहते हैं, ये comments line कहते हैं. So when you put this sign percent sign at the start, you can guide yourself, because later on if you see the program you should be able to understand what was the command given after that. जब command देनी है वो black color में आएगी, there will be the no initial any sign given for the command. So this is a command line, and this is the comment line. Now how can you write down the command? Let's say the initial displacement is given as u naught is 1, and initial velocity is also given. So these are the initial conditions for the response of the system. Now you have defined the period and frequency. You have the time period. You can give them some value. This is for the one of the problem which was solved. So time period is 0.5 and omega आप निकाल सकते हैं. The angular frequency. What is the formula? 2 pi over t. तो MATLAB में कैसे लिखेंगे? 2 steric for multiplication, and pi जो है वो straight away आप pi लिखेंगे. तो MATLAB will pick the value of the pi. और time period आपके पास given है, तो इससे क्या आ जाएगा? ओमेगा. तो time period is computed, natural time period and the natural frequency आपके पास आ जाएगा. नेक्स्ट यू हैव टू डेवलप अ टाइम वेक्टर, क्योंकि आप खुद से टाइम वेक्टर बनाना चाह रहे हैं. यू डोंट नो कि टाइम जो है आपके पास स्मॉल इंटरवल भी हो, ये काफ़ी स्मॉल होना चाहिए सो दैट एवरी पॉइंट कैन बी प्लॉटेड. So you can select very here, like say total time of the vibration was the 5 seconds. So t linspace, this command is given for generating a linear vector. Time vector is the linear space vector, which is starting with the 0 second, ending with the 5 second. और 500 आपने इसके कर दिए हैं कि 500 values का you can generate the vector of the 500 values. So t is equal to linspace 0, 5 and 500. So in this way you can generate the time vector. Next is the calculate the displacement response. अब आपको पता है कि a की वैल्यू क्या होती है, the constant जो होते हैं a is equal to u naught, दोनों present है ना. पहला केस आप देखेंगे, so you will see the first case because u naught and v naught both are present. So what was the a value? A was the u naught and what was the b value? B was the v naught over omega. ये वाला केस है, तो a और b की वैल्यूज आपको दोनों मालूम है. So you can go to that and you can put down the value of a. A is the basically calculating the response, so you need the constants. A is u naught, equation भी इसमें बताई गई है बुक से, and b is equal to v naught over omega. तो बहुत सिंपल है मैटलैब. आप स्लैश यूज करते हैं डिवाइड के लिए, स्टैरिक यूज करते हैं मल्टीप्लिकेशन के लिए, और इसमें आपको वेक्टर बनाने के लिए अरे नहीं बनाना पड़ता. आप स्ट्रेट अवे ये टाइम जो t जो है ये वेक्टर है, ये 500 वैल्यूज का वेक्टर बन गया. अब आप इसमें कंप्यूट करेंगे u रिस्पांस ऑफ द सिस्टम. तो u इज इक्वल टू a cos ओमेगा t प्लस b sin ओमेगा t, ये फार्मूला था. So you can put down the values. Now u answer will not be a single value. Why? Because time is a vector. यहाँ भी time vector है. A and b are the single value numeric constants, but t is a vector. Omega t is a vector. So cos of omega t or sin of omega t is a vector. So answer will be in the vector form equal to the 500 values. आपकी 500 values आ जाएंगी u की against every time value. And then you can plot the amplitude. आप निकाल सकते हैं. Amplitude is c. After that you can determine the c value and then u dot क्या है, ये velocity है. You can determine the u naught and now you can plot the values. u naught और omega भी निकाल लें, divided by omega कर दें तो u naught और omega आ जाएगा. You have the amplitude. Now you can plot all the responses. जो भी आपने करने हैं, आपको मैंने आज जो बताए हैं, आप you can plot all the response. This response of the ये वाला केस है ना हमारा, you can plot this response because you have all the parameters. So you have determined all these parameters, so you can plot different response. U naught over omega. So plot at the moment one is the one value is plotted, and you can plot more values also.
In this way, you can plot the system and then you can get the different values. So try work on it. And because how to plot in the MATLAB, plot की command is simply t versus u. Time on the x-axis आएगा पहला, u is the displacement, so you can get this response. Similarly, जो बाकी graphs हैं, you can also obtain the remaining graphs. So try working on it and plot the different parameters. And it is really helpful. And from the learning point of view, what we have discussed today about the free vibration response of the single degree of freedom system. Try practicing all this chapter and problems, and also in the MATLAB, try to work on it. So if you have any query now, because maybe I should not start the new topic, maybe next time we should start the damped single degree of freedom. पहले आप जो है इसको complete कर लें, तो हम फिर next start करेंगे. If you have any questions, you can ask, please. Do you have any question?
No, sir.
No, sir.
So please ask one by one the different questions, and then we can